Plattsburgh Fieldhouse, and we're going to talk about hockey with you. We are going to go over some SUNY Plattsburgh hockey, but first I'm going to give you some general hockey facts. So, historical references show that crude forms of hockey have existed in Iran since about 2000 BC, Ethiopia 1000 BC, and Egypt 4,000 years ago. Hockey is a crossover sport of English field hockey and Native American lacrosse that was created in the mid-18th century. On November 26, 1917, the NHL was created, National Hockey League, in Montreal, Canada. And the original six of the NHL include the Montreal Canadiens, the Toronto Maple Leafs, the Boston Bruins, the Detroit Red Wings, Chicago Blackhawks, and the New York Rangers. So, in December 12th, 1933, there was actually an accident between two of the original six teams. The accident included Ace Bailey and Eddie Shore. Ace Bailey was a player from the Maple Leafs, and Eddie Shore was a player from the Boston Bruins. What ended up happening was that Shore actually hit Bailey from behind. When he hit Bailey, he was left with a brain injury, and Bailey unfortunately was left on the ice, unconscious and twitching, and it completely ended his career. After the incident, Art Ross created a new helmet design, but the design of the helmet was very unpopular with both fans, players, and the media. Not many players wore the helmets at first, so it was really a weird situation that they were in. Of course, we wanted the players to be safe, but helmets were not looked at as cool. It wasn't until after the death of Bill Matterson on January 13th of 1968 that the perception of helmets began to change. He died from a brain injury. He was not wearing a helmet, and he was from the Minnesota North Stars. So after that incident, helmets became more popular with both players and fans. And 11 years later after the incident, in 1979, about 70% of NHL players began to wear helmets. So safety is really important, and therefore we're going to go switch over to Matt, and he's going to talk about more about safety and what happens when players collide and why exactly helmets are important for that reason.
So as Deanna was saying, safety is a very important part of hockey, but in order to understand safety, we must understand the physics of basic collisions. In physics, there are two types of collisions: elastic collisions and inelastic collisions. Collisions are directly related to momentum, which is a conserved quantity in physics. Right here with an elastic collision, the two players will bounce off each other, and in inelastic collisions, we're talking about two players that come together and they stick together, and they'll go out at the same speed. So here's an example of an elastic collision. Let's say that we have one massive player as mass 1, and we have a smaller player, mass 2. Those two players will come together, they'll bounce off each other, and the player that with more mass will exit with a slower velocity because he's heavier. In mass 2, this guy will leave with a faster velocity. With an inelastic collision, the two players will come together and they'll stick to each other. So this could be like a player comes in, they press each other to the glass, and the masses will combine and they'll have the same final velocity. So we have a quick demonstration here of what this looks like with an air track. So now to model an elastic collision and an inelastic collision in real life, we have an air track and two carts. So the air track will be like our hockey rink. This will have very low friction when the air turns on. I'll turn it on right now. So as you can see, the cars move easily along the track because there's low friction, just like on a real ice hockey rink. So we'll have these carts right here be like our hockey players. This cart has less mass. This will represent a less massive hockey player. This cart is weighted because it has weights on both sides. And this will represent a more massive hockey player. So on one end, we have rubber bands on both sides. When these two rubber bands come together, this will represent an elastic collision. On the other end, though, we have us end with clay, and we've got an end with a needle. The needle will stick into the clay, and this will represent an inelastic collision. So now I'll model an elastic collision. So here's a very common scenario for an elastic collision. We have two hockey players. One will be at rest, and one will come in with a speed and collide with the other player. So right here is a demonstration. The more massive player right now is at rest, and we'll have the less massive player come in with some speed. So here we go. So as you can see, the less massive player transfers momentum to the more massive player, and they bounce off each other. The more massive player bounces off down the track. Momentum is still conserved. So now I'll show you a demonstration when both come in at different speeds. So as you can see, they both bounce off each other and go in different directions. This is an example of an elastic collision where they both have initial speed coming in and colliding with each other. So now I'll model an inelastic collision with the clay. So now we'll have the more massive hockey player stay at rest, and we'll have this less massive hockey player over here come after him with a speed. So as you can see, both hockey players stick together, which is the reason why we combine the masses, and they both exit with the same velocity because they're connected together. So now I'll show you one more demonstration. Both hockey players are going to come at each other with some speed, and we'll see how this affects the situation here. So as you can see, they collide together, and they come to rest. This is an example of a perfect inelastic collision. They both come together, and there's no speed at the end. So now we're back at the board now from our demonstration here, and I'm going to describe why elastic collisions, and momentum all play an important role in designing safety equipment. So the goal of safety equipment is to absorb as much shock or as much force as possible, so players naturally don't get concussions and don't get injured. So what we have here is a concept. They're two interrelated concepts. They're called impulse and change in momentum. So impulse, what we do, we represent this by the letter J. I put an arrow over it because it's a vector. It has magnitude and a direction. And this is equal to a force, which is another vector, magnitude and direction, times a change in time. So when two players collide, we have an impulse, an impact. This is the shock. This is a force. And this is how much time that the collision happens with. So if these two quantities are inversely proportional, so we have a large force, that means that the time of impact is very small. If we have a small force, the time of impact is very large. So that's why there's a lot of padding on objects, or safety equipment and helmets. When there's a lot of padding, we increase the amount of time of impact, and the force decreases. So this is also related to a concept called the change in momentum. So the change in momentum is represented by a delta P right here. It's the same thing as up here, just the only thing is we're changing the momentum. In order to change the momentum of a system, you have to increase or increase or decrease the velocity. So in order to change the speed of something, we naturally have to put a force on something. So if you push or pull something, you're going to change the speed of it. So naturally, with large impulses, we have a large change in momentum. So that means we apply a big force. And with small impulses, we have small forces, we have small change in momentums. We want hockey players to experience a small change in momentum to avoid an injury.
Okay, so I'm here today to talk to you guys about all the formulas that Matt wrote earlier and how to use them in practicality. So first we're going to start with the elastic formula, then we're going to go to the inelastic one. To solve for the first equation, I've already rewritten it here, which is always a good first step in math, is to rewrite the equation you're using. Some notes about this equation. The I here stands for initial. Since it's referencing velocity, it's the first, or the one here is the first person. So first person's initial velocity, second person's initial velocity, and then over here the F is for final. So first person's final velocity, second person's final velocity. Now this equation, as Matt mentioned earlier, is for when two people run into each other and then bounce off each other. So I'm going to set this up and show you guys how we go about solving this should you ever need to. So we're going to say the first hockey player, we're going to say he has a mass of 60 kilograms. So we write in 60 kilograms. The parentheses are used to show when two things are going to be multiplied together. As shown in the equation, we're going to multiply it by his velocity. Let's pretend that this guy is stationary. He's not moving. Plus, there we go, mass of the second person. Let's say they're a little bit more massy, so we're going to get 80 kilograms times their initial velocity. Let's say they're moving at about 5 meters per second. Now, this is going to equal their final velocity, and mass stays the same since they didn't lose any weight between the two moments. So mass of the first guy still 60 kilograms. In this equation, we're going to want to try to figure out what his final velocity is. So for now, I'm just going to leave this as V1F because we don't know what it is yet. Plus mass of the second guy, still the same, 80. Final velocity, let's say he bounced off and he's now moving at like 2 meters per second. From here, the equation is pretty simple algebra. This 60 times 0 is going to be 0. 80 times 5 is going to be 400. So we go plus 400 equals 60 times, we don't know yet, so that's going to stay the same. 60 times E1F plus 80 times 2, which is going to be 160. So then we get 400 equals 60 V1F plus 160. We want to get this all by itself, so we're going to subtract 160 over. Minus 160. We're going to get 240. 240. So we get 240 equals 60 V1F. Divide by 60. The answer, which I'm going to write over here, is going to be a 4 meters per second. So what this is telling us, a couple things actually. So, how do I phrase this? Velocity has a vector with it. A vector quantity is something that has a amount to it plus a direction. So if we want to use an example and say the wind today is blowing 30 miles per hour west, that's a vector. If we just said it was blowing 30 miles per hour, it's not a vector, it's just a quantity. In this case, since the second person's velocity was positive and the first person's velocity is positive, they end up going in the same direction at the end. So the second person hit the first person with enough force where he bounced the same way the second person was going, and the second person is still going that direction at 2 meters per second. That's how we get through this first equation, and that's how we use it to find different answers. I'm going to erase all this, and then we'll go on to the second problem. Okay, so now I'm back with the second equation. This is for the inelastic collision equation. What this is representing, as Matt mentioned, is when two hockey players come together and then stay together. So we're going to use the same numbers we did last time, this time with a black marker. So these represent same things as before: mass of the first person, initial velocity of the first person plus mass of the second person times the initial velocity of the second person. So the first person we said was 60 kilograms times their initial velocity, which was 0, plus mass of the second person we said was a little heavier at 80 kilograms times their velocity, which was 5 meters per second, equals mass of the first person stays the same, 60 kilograms. Nope, that's my mistake. It's a plus. Mass of the second person, 80. We don't know what the final velocity is. That's what we're going to try to figure out. So this stays as VF, velocity of final velocity. 60 times 0 is still 0. Plus 80 times 5 is going to be 400 equals 60 plus 80. Let's see here. That is going to be 140 times final velocity. So just to simplify, 400 equals 140 VF. Now to get V of F, or VF by itself, we have to divide by 140. This works out to be about 2.86 meters per second. So what this is telling us is that when the second person ran into the first person, they stuck together, and both of them are now moving 2.86 meters per second in a positive direction in this case.
All right, guys, thanks for that information. So now we're back at the SUNY Plattsburgh field house. We're going to talk about the men's team. So the men's team was created in 1976, and for the 42 years that they've been a team, they've played in 902 games. Out of those games, they've won 649 games, lost 207, and have tied in 46 games. In 1992, the team started playing in the SUNYACs with their current coach, Bob Emery. The stats show that 1992 and 2001 teams have been the best teams. In 1992, they won 32 games, lost 2, and tied 2. That year, they also won the NCAA championship. In 2001, the team won 29 games, and they lost 5. Many players from both of those teams have been inducted into SUNY Plattsburgh's Hall of Fame. So that's really cool. So now we're actually going to switch over and we're going to talk about the girls. All right, and now we're talking about the women's team. So the team was created in 2001 and they've played 14 seasons. Since they started playing, they've played in 411 games. They've won 344, lost 44, and have tied in 23. They're also in a completely different league than the men's hockey who play in the SUNYAC. The women's instead play in the ECAC, also known as the Eastern College Athletic Conference. In that conference, they've won 7 conference titles, 5 straight in a row. They've also won 4 consecutive national titles and 6 in total since the team has been around. Alright, so that was an awesome game we just saw. It was St. Michael's College versus SUNY Plattsburgh, and we ended up winning 6-3. So game recap, we actually had 3 goals in the first period. First goal was at 2 minutes and 17 seconds by sophomore Bo. Then we had a goal at 6 minutes 57 seconds in by senior Engvall. And 37 seconds later, Owens, who's also a senior, scored again on a power play 6-5. About 8 minutes 22 seconds in, St. Michael's College answered. Then that period was a little violent, kept going on. Second period starts. St. Michael's College scored at 6 minutes and 19 seconds. we answered our game-winning goal at 12 minutes and 32 seconds with sophomore McCartney, who also scored again then at 17 minutes and 2 seconds on a power play, 6-4. So that was awesome. Period ends. Third period, we score again at 3 minutes and 36 seconds in with senior Sloan. And then St. Michael's College answered at 9 minutes and 24 seconds. The rest of the game was very violent, a lot of penalties, but SUNY Plattsburgh still ended up pulling it out. So that's all we have for you. We hope you learned something, and we wish we could have brought you into the game, but hope you enjoy the little clips we have. See ya.